what I'm going to do here is that I'm going to be deriving length contraction. That's sort of like the goal of what I want to do here. And one of the things that I want to remind you is I want to remind you about the Lorentz boost here. So when I think about Lorentz boost, we're really talking about two things. And we're only talking about one-dimensional boost transformations. And so what I mean by these one-dimensional boost transformations is that we don't account for y and z. We're only looking along the x direction. So what we said here is that if I write down that I'm going from s to s prime, what that really means is that we could talk about single coordinate systems, but that's a meaningless statement. One position measurement doesn't mean shit. One time measurement doesn't mean anything. The only thing that we care about is we care about the changes in time and changes in distance, right? There's our spatial one. And then, of course, if I look at my time, the same thing happens. Oops, that's a minus sign. I get something like this here. And physically, what we talked about last time is that I imagine that I have an observer. And this observer is in this pale blue dot. I don't know what you know what I mean. I expect you may have heard of the expression pale blue dot, right? That's none other than Mr. Carl Sagan. And I love that quote that he always used to use here. And we imagine we have some dude here, and he's in some frame S. Now he's observing what? He's observing some rocket moving away. And of course, this rocket is the other observer. And so when I think about this other observer, we consider that frame to be the S prime frame. And what we know about this S prime frame is that it's moving relative to the S observer here. So what this Lorentz boost does is it takes this S observer and essentially boosts it into the prime observer. And we said we could go the other direction. And if we do the exact same thing, all we do here is that we change the plus where the minus are, and we switch the primes. So it's the exact same thing, except that this time the observer sees the other one go the opposite direction. Right? No difference here. So in this case, when I think about the Earth here, it's the Earth, or this S observer, that is moving. And what's happening in the rocket frame? In the rocket frame, they are stationary. Of course, they cannot say that they're at rest or moving. So then this observer here is observing what's happening in the S frame. And what I want to do here is that I want to go in and I want to focus on this one here. So I want to look at the length contraction of S prime looking at S. So I want to do it just the opposite of what, a lot of times people think about. So the important thing here, of course, is that when I look at the principle of relativity, one cannot claim they are at, right? That they are at rest / constant velocity. You cannot state that. the systems, the two are absolutely symmetric between each other here. So what we want to do now is that I want to come in and I want to derive the length contraction for Maria in the S prime frame is going to see Juan's meter stick. Maybe I should be a little bit more careful here. So if I look at Maria's meter stick, right, her meter stick is 1 meter in her frame of reference, right? That's what we call the proper length. Why is it the proper length? Because the meter stick is at rest relative to Maria, or the S prime observer. And what we expect then is that for Juan, that he's going to see what? A different meter stick. And his meter stick, oops, my bad. His meter stick, of course, is going to be length contracted. And so when we look at his length, we should see that the X should be smaller than the X prime. That's what we mean by this length contracted. But there's a subtlety here that we have to really address here. What we assume here, when we make this calculation, so the assumption is as follows here. We assume the measurement is made of both ends simultaneously. And that's no surprise here, because if you take a meter stick and you ask yourself, well, what's the length of this meter stick? You look at both ends and you go like, wow, it's a meter. So what this implies here is that because of this, we're going to say that in Juan's frame of reference, that time difference is 0. And that's a pretty normal thing here. But let me tell you why this is a real big issue here. Why is this a big issue? So now let's talk about another system here. So this is a real problem with most textbook problems. And you might be saying the following thing. Let's say that I have some observer. And by the way, this is sort of like one of the conceptual questions that you're seeing. And you're going to some other planet. You're going to this planet here because it's what? It's very lush and green here. Okay? So now what you're finding here is that now you have the spaceship that's moving. And as the spaceship is moving in this direction here, what we have to worry about is we have to worry about the length contraction between these two very far spatial locations. So let me ask you this question. Can you make those two measurements simultaneously? Hell no, you can't.
No, you can't.
As a consequence, this delta t is not equal to 0. But textbooks will say, well, we're going to assume that you could make these two measurements simultaneously. Why? Because this frame and that frame are in the same inertial frame, and so therefore you should be able to make time simultaneously between these two clocks being in sync beforehand. Well, there's a lot of trouble with that. And that's why I'm saying that this is only true, okay? This thing is only true for special conditions here. So you got to imagine that you're going to hold something and just go like, okay, this is how far apart it is. I got it now. So I could see that. But if you're talking about spatial distances that are relatively far, that means that the speed of light is going to take, some fraction of time. You can't make that statement. So let's keep moving. So if we're going to make that statement here, so now let's go look at this. And what I want to do here is that now I want to come here and I want to start talking about what do I mean by a measurement. So what we find here is that the proper length when both observers are in the same inertial frames is that they both measure the same meter stick. So what do I mean by that? Well, I have one meter stick, let's say it looks like this, and I have another meter stick that looks like this, and they're both, of course, the same length. So if I'm thinking about, let's say, Juan's meter stick versus Maria's meter stick, right? We're saying that in this case here, I'm going to call this x1 prime. I'm going to call that x2 prime. I'm going to call this x1, this x2. So when I make these measurements, that means that I have a space measurement. By the way, I should be a little bit more careful. Maybe I should put times here. Right, so the coordinates of both of these here tell me that I could make space and time measurements like this. So I could talk about, time dilation. Here I'm just talking about length contraction, and that's because of the way the gamma sign. By the way, just by me writing the Lorentz transformation for time and showing that this is what it is, it's technically incorrect what I did. You have to do exactly what I'm doing now. So now what we're doing here is that I now have two observers, right? What are the observers that I'm talking about? I'm talking about this situation now. Oops, bad. So what I'm looking at is I'm really looking at these guys right here. Okay, something's funny here. So I'm really looking at this frame right here. And so what I want to do now is that I want to come in and I want to really pay attention here. So now, here we go. So we assume delta t, which is t2 minus t1, is 0. That Juan can make simultaneously time measurements between the two ends. So here I go. So now, what I'm going to do now is that I'm going to boost from the prime to the s. And when I do that, what that really means here is that if I look at lengths, we know that this has to be this case here. And we also know that I can't not talk about time. I must talk about time. Okay? I must talk about time. By the way, I think I need plus signs here, right? So then I'm going to get VC squared delta T prime here. It doesn't really matter whether I have plus or minus signs because each of these frames are identical, right? I can't say that this one's the right frame or that one's this. The other one's going to give me a minus sign if I put the plus sign in here, but it gives me the exact same relationship. So now what we find here is that we assume this, and one of the things that I forgot here is that we assume that this is not equal to 0. So now, if I make a time measurement, so the single time measurement.
Hey, Carlos.
Yeah?
That equation, your delta t equation, the second delta t prime, shouldn't that be a delta x prime?
Yes. Yep, it should be a delta. Thank you. And so what you're going to do here is that for a single time, what I really mean here is that if I start with T1, and then I'm going to boost from the prime, then this is going to be gamma, which will be T1 prime minus gamma V C squared X prime 1. Right? That's what I mean by a Lorentz time. Because note, this is not 0. I have to account for that time. We already said that in the prime frame, the time is not 0. So now what I'm going to do here is that then I could come in and go like, but I know the time difference because this is really T2 minus T1, which then should give me 0. I could make simultaneously measurements between those two spots. So then this should give me gamma delta T prime minus gamma V C squared delta X prime, which then tells me that if I solve for delta T prime, this is going to be V C squared delta X prime. So what I've done here is that I've now calculated a time measured by Maria that is not simultaneous, right? So this is a non-zero value. And if you tried to do this with the Lorentz transformations, you would run into trouble because you're including a mixture of time and space, but you gotta isolate the distance. So now if I keep going along here, what I'm gonna do is that now that I have that, so now I focus on the length of Juan, which is the S frame. So if I do that, we already said that this guy was equal to what? Gamma delta X prime minus V delta T prime. But you could see then that I got to come in and I got to put this guy here with delta T prime is then going to be V C squared delta X prime. And if I put that in, what you're seeing here is that I'm getting gamma. Then I'm going to get, of course, delta X prime minus, look at the V squared here now. There's one V right here. There's another V right here. So when I put those in, I'm going to get a V squared. I'm going to get V squared C squared delta X prime. So now I start factoring things out. Now I'm going to write out gamma. Gamma is what? 1 minus V squared C squared square root. And then in this term here, I get 1 minus V squared C squared. And then I pull out the delta X prime. And if you look at that, one of these cancels. So then I get that delta X is then going to be what? 1 minus V squared C squared square root delta X prime, or delta X prime over gamma, which is delta X. In other words, this tells us that Maria sees Juan's meter stick length contracted. Okay. Oh, that did, I don't know what I spelt right there. It's length contracted. That's how you would derive that. And so just to give you a sense of this length contraction, what this means here is that
Hey, Carlos, could you scroll up for a sec, please? So I can get
Yes.
to the last slide. Thank you.
Okay. So if I was you, I find this very disturbing. Right? Why is this disturbing? Well, I think for me, the reason why this is disturbing here is that any inertial observer will always measure different lengths. They will always measure different lengths, no matter what. That means I'm always going to get delta x not equal to delta x prime.
Um, Professor, so when that person sees that person do that time, do they see that that person's like both times? Because I thought like when that that I mean in terms of the link contraction, you can't actually see that. I mean how?
Well,
Like,
what do you mean you can't see that length contraction? I mean,
I mean
you could measure it if that's what you mean,
yeah,
but the way you measure it is that you have to look at other things. You can't race up and take a meter stick and just say, oh, your meter stick is smaller than mine, because then you're in the same inertial frame of reference and the meter sticks are going to be exactly the same.
Oh, okay.
But what you conclude here is that if you go like some distance and you see how long it took them,
Oh,
you know, like how much time, you have to conclude that there must have been some type of length contraction.
okay.
So you could not, it would have to be an inference. And here's the sad thing about that, is that both observers are right. And like I said, this is something that has hounded me for decades. I cannot tell you how many times, like I've said before, you know, if I look at the accelerator at Slack, it's 2 miles. How many times have I said this before? You know, here I am, you know, running along this thing here, and I'm saying, yeah, I just ran 2 miles. And I laugh at myself and go like, that's bullshit. What I'm saying is absolutely bullshit. It's not true. And how can you not conclude, you know, how could you not conclude that that's not bullshit? But it is. Okay? It is. It's not, it's my problem. Right? It's my problem that I don't want to accept that to the electron sees this little tiny thing. Right? So from the electron's viewpoint, it's actually doing this type of thing. It sees that length. And it's a really, really surprising factor here, but I mean, we can look at this thing. And if you look at this here, so in the lab frame, what I know here is that beta is 0.99999996. That's the speed of light that the electrons move effectively. Now note that this is a little bit of a white lie. This is the final speed, but electrons are accelerated. So if you could get the electrons to actually move this fast, like the whole way through, then this is what you get. You'd find that gamma, which is 1 minus beta squared, would then be this 1 minus 0.999996 squared. And you get a contraction that's, I know that's 4 sig figs, but I'm just trying to get you to look at these numbers here. And then when you go and you calculate the length contraction, for what we just did, well, 2 miles is 5,280 feet, but we have 2 of these, and then you get this length contraction. And what you find here is that this guy is really 9.5 feet. But one of the things that I said here is that there's acceleration of electrons, which means that you got to bring in the general theory of relativity. And when you look at the general theory of relativity and you account for all of these things here, that means you essentially get something like this. You get a piece that deals with special relativity. You get a piece that deals with general relativity. And then you have a gamma factor that's a function of velocity that's changing. And when you calculate that whole thing, then you get this 3 feet. And like my running joke, you know, back in the day, I'd run by that and I'd go like, it really is 2 miles long. I can feel this thing as I'm running around this thing. And then, like I said, I just start laughing at myself. What do you mean it's 2 miles long? It's not 2 miles long. Space and time measurements are what? Have no objective reality. Different inertial observers measures different space intervals and time intervals. By me saying that the accelerator is really 2 miles long, I am violating the principle of relativity. I'm precluding that, saying that my frame of reference is the right frame of reference. It's not the right frame of reference. If you're an inertial frame of reference, all measurers are correct. And that's the hard thing to really understand. This is sort of like where I'm saying, you know, if you're in your mind going like, yeah, I get you, Carlos, I understand that. I'm saying you've now taken the blue pill and you're bullshitting yourself because, or else you're mentally dead, because when I look at this thing, I'm going like, this is no way could this be true. I'm saying this is the preferred frame. It is 2 miles long. I don't give a damn what anybody says, but that's not right. And I know it's not right. And there's times, you know, in certain situations, I'll be in bed at night and I'm going like, I know the world can't be this way. It cannot be this way. It is. That's the problem. It is this way. And it's not my fault that your intuition and common sense are being attacked. That's your problem, not mine. I have my own problems I got to deal with. And that's what you got to remember, that this stuff is disturbing. And it gets worse as we get along. Wait till we get to the next chapter when we really start talking about massless particles. So what I want to do here is that I want to move in and I want to lightly go over these things called.
Carlos, I have a question.
Yes.
So maybe, so when we have length contraction in terms of in the frame of reference of the electron, at slack.
Uh-huh.
That's because space-time wants to keep c a constant, right?
Yeah.
That's what.
But C's not the only invariant. The other invariant is the relative speed. Because if we're moving at constant velocity, both observers are going to measure the other moving at the same speed. So there is a symmetry, right? So what I mean by that, so if I'm looking at this, I agree that speed is the same, right, for all observers. Now note, I'm not saying velocity. They have different velocities, but they have the same speed. And what I'm saying here is that the relative speed, which is going to be the more important thing, this is the same for this observer as well as that observer. So in essence, this is also an invariant. And right now in this chapter, we're not really talking about invariance, even though we should be. I mean, this special theory of relativity, I think, is a terrible name. Because we don't care about things that have no objective reality. We only care about things that have objective reality. And what I mean by that is that we want the same things that all measurers measure. And those are called invariants. And Einstein later on tried to change his wording for the theory of relativity to the invariance theory. But it was too late. So we're stuck with special theory of relativity. We should be dealing with invariant theory and what's invariant in all of these processes. So let's talk about space-time diagrams because it's a visual aid to looking at Lorentz transformations. So if I look at this, space-time diagrams are a visual aid for Lorentz transformations. Slash boosts. Okay, it's a visual aid. And the beauty of these space-time diagrams here is that you can plot multiple frames of reference on a single plot. However, the cost is they can get very tricky very fast. So most of the time, we don't care about plotting multiple frames of reference. Sometimes it's useful, but it's not worth it because otherwise you spend a lot of time trying to decipher what that is. And the bottom line is this: we're only interested in one thing in this course, and that's the physics. If the space-time diagrams help with the physics, then we plot them. If they're confusing the issue, we don't plot them. That's simple. I only care about the physics. I think of space-time diagrams as a tool like a calculator or a position, velocity, acceleration curves in kinematics. It's just a tool to understanding deeper what's going on. So what I'm going to do here is that I'm going to call this a summary. Because we could mathematically write this stuff down, but oh my, we'd be here for a while. And we don't want to do that. You can calculate all of the details, but we don't want to do that. We're a user of space-time diagrams. Okay, so here's the first thing that I want to look at. So the first thing that I want to do here is that, so we can plot position curves in kinematics. And if you plot position curves, what do we know? Well, we have a curve. We typically write position versus time. And we can have some slope here. And what do we know about the slope? Well, the slope tells us about the speed or the velocity of this curve here. Now, the thing about this is that this line here, what it really does here is that it represents a trajectory. Okay, it represents a trajectory. Now, what is the space-time diagram? So if I look at a space-time, we also have a plot that we're doing, but there's a difference there. What they do that's different is that they reverse time and position. And so on this curve, if we have a curve like this, which we do in special relativity, the slope of this curve, of course, means that it's the reverse here. That means that the slope is 1 over the velocity. So we're looking at the slopes of curves given by this. But what do they call this line? Well, a trajectory in space-time is called a world line. Boy, I think that word is so awesome. A world line. Why didn't they call trajectories world lines, right? It's as you move through the world. And so, you know, a lot of the same type of things that we would expect here is that all lines in space-time diagram are linear lines. Why are they linear lines? Because there's no acceleration. This implies that v is always a constant, which of course means acceleration is 0. That's the definition of space-time, right? All lines are linear in nature here. So then if I start to look at this thing here, if I look at the slope of this line, so if I have a second slope here, let's say if I compare something that's steep like this, so a steep line, a steeper slope implies what? A lower v. Whereas a less steep implies a higher v. So the less steep the line is, the faster it's going. However, there's something that I haven't said here, and it really does, you know, what you find here is that the maximum speed is c. And in this world, what you're going to find here is that when I go and I plot these, that means that our speed, c, is always at a 45 degrees. So this is v equal to c, and it's at an angle of 45 degrees. So this guy's at 45 degrees. So any world line.
Delta t over delta t, you meant delta t over delta x.
Say that one more time.
You put slope as 1 over v is, and you meant to put delta.
Oh, yes. Thank you. Yeah, that should have been delta x. Oh, man. Thanks for the correction.
Sure.
So you could see that in space-time, any world line has to be along here. So what we're saying here is that no world line can travel at C unless massless. Okay? So that's what we're saying right there. So speed of light, so that means when you draw these, you do that. Now, so let's look at the next piece here. So the next thing that I want to do here is that to sort of like summarize these guys here. So we have a light cone. And the light cone essentially implies that if I look at this light cone, these world lines are going to be symmetric. And so if I look at light, I'm going to see that this light here is at 45 degrees and it goes all the way back. And then I have another. And so what we're really saying here is that this is essentially what they call the light cone, right in this region right there. So of course, this means V equals to C. And of course, this equals V equal to C, but in the negative direction. And what you're finding here is that in this region, this is the future. You can influence. And this is the past. You can influence. But in these regions over here, right, we're talking about this red region. What you find here is that in this red region, this is the future, and this is the past that you cannot influence.
What do you mean by influence?
There's a lot of ways to say that. Let's say that, okay. See, goddamn it, Manuel, now I gotta answer your question. So let's say you're here on Earth, okay? You're on the pale blue dot here. Okay, and this is you, Manuel, or Emmanuel, like the singer, huh? So what you find here is that you could imagine that this is Mars. Right, and of course Mars is the red planet. So what you find here is that, let's say that you're in communication with one of the rovers and somebody's on Mars. So if you're looking, maybe you see this territory right here, and you're standing right here. No, not you, but this is your friend. Why not? Your friend Jason. So Jason's right here. And what happens is that there's the rover is coming over. And right now at the moment, it takes what? What's the time? Is it like is it a minute? No, 15 minutes? 13 minutes?
14 minutes.
14 minutes. So that means if you communicate, right, it takes 14 minutes. So what happens is that Jason sends you a communication. Now, because these guys are traveling at speed equals to C, the fastest that you can communicate is at C. So now Jason sends you this image, and you get that image, and you're telling Jason, hey, Jason, watch out behind you. What's going to happen? Well, you can't communicate. You can't communicate, right? You can't communicate. Eventually, this is the past. It's going to come elsewhere. But what happens here is that this region is known as the elsewheres. But I should be really careful because the example that I gave you, that if you had enough time, you could tell Jason, hey, watch out behind you. And then this thing could do what? It could come from the past and into the future. But this thing, before it actually happens, while it's not in your past, it's not in your future, where is it? It's elsewhere. We don't know where it's at. But this thing can actually do what? It can actually move into this region right here, into your future. It's just that you can't do anything about it at that time. Okay. So in essence, this line right here represents the future and the past. Okay, let's go to the next piece. Now, the next piece that we should lightly talk about is that, let's talk about the Lorentz boost. So a Lorentz boosts form orthogonal. How do you spell orthogonal? If I spell it wrong, it's okay.
That's good enough.
Orthogonal coordinate system.
What about paths that can influence you instead of paths that you can influence? I'm not aware of being able to influence the past.
What do you mean? No,
Like
you
the one-
can't, but the past can influence your future. But
Right.
you're right.
So maybe the wording that you chose was like backwards. Like paths
Oh,
that
I don't doubt it. Okay, if I said that, okay,
Well,
so
Carlos, you wrote in the light cone past you can influence. I think we're wondering, like, how can you influence the past?
the way you influence the past is that as it moves into your future light cone. Maybe that's not the right way to say it. I can see what you're saying.
paths that can influence you.
The past that it can influence you.
Yeah.
That's what I meant to say right there,
That makes more sense.
right? Past that can influence you. That's what I meant to say. Thank you, Jason. So I have an orthogonal coordinate system like this. That looks a little bit funny to me, but I shouldn't really pay attention to those details. So they form a coordinate system that's orthogonal. Okay, that's super important. So let's look at that. So if I look at the S frame is typically taken by plotting this guy here. And so when I look at that coordinate system, we typically imagine sort of like the standard things like this. So I have a grid system that all of these are orthogonal to each other. Okay, so I would say that the S frame is typically the standard one. But if you look at the Lorentz boost, though, they're not linear equations. So what happens here, if I look at the S prime frame, their coordinate system is skewed. So the S frame has coordinates that appear skewed. So in other words, if I look at the red one, I could imagine that it's like this, where this is t and this is x. But now, if I look at the primed frame, they're skewed, but don't let that mislead you, because they're still what? Orthogonal coordinate systems. So then that means if you were to derive these, you could show that these are all, even though they look skewed, they're orthogonal nonetheless. So they form a right angle in this coordinate system. If I could say right angle, right? Right angle is really not the right word to use, but that's what I mean by that. And so what I want to do here is that it's essentially how we can draw two different coordinate systems here. Now note, if I brought in these sort of like red coordinate grid system and I put it into this one, it gets real messy right away. So in this course, my job is not to try to plot both of these simultaneously because it could get quite ugly. And so what you typically find here is that you get the following thing here, is that the skewing
Hey, Carlos,
coordinates.
your audio went.
Did it go?
I'm not sure if you were speaking like 10 seconds ago.
You know what? I put my head down as I was writing. Can you hear me okay?
Yeah, it seems fine.
Yeah, you're good now.
Okay, then I'll try not to keep my head down. So the skewed coordinates depend on speed. So in other words, if I have a coordinate system like this, and if I move, let's say and this guy moves at, let's say, 50% C, in other words, beta is equal to 0.5, then the coordinate system looks like that. If I go faster, then this guy here gets closer to the speed of light line. So in this case, so this is V equals to C, so this purple line here, what that represents, let's say that this is beta equal to 80% C. So as you get closer and closer and closer, these lines move closer and closer together to each other. Only at C do these two coordinates line up with C. So that's one thing that you want to remember, that they depend on the velocity. And so then the last thing that, maybe not the last thing, I want to do two more things here. The thing that we should talk about here is that our preferred units in space-time is not T, but CT. Okay? It's CT that we want, not T. And there's a very, very good reason why. So let's think about this here. So the time for light to travel 1 meter is what? Well, we get C is equal to delta X over delta T. So if I look at this guy here, it's going to be 1 meter times the speed of light. And this is going to be about 3 times 10 to the negative 9 seconds, or 3 nanoseconds. Now imagine trying to put this into a coordinate system, right? So try putting this into the plot. Wow, that's horrible. That is horrible units. So the way we do this here is that we measure time in the distance that light travels. So now what we do here is that so instead of T, we use CT, which is the distance light travels. So that means for a 1 meter stick, we know that C is equal to delta X delta T. So then if I write CT like this, then that means that what I'm really measuring, I'm saying that this is 1 meter. So CT is 1 meter, and this is much nicer to actually write that down instead of something of the order of 10 to the negative 9 seconds here. So when we plot space-time diagrams, so then our coordinates for space-time diagrams should be CT and X, not T. And that's the reason why we do that. So now the question is, what is Lorentz transformations? Okay, what do I mean by a Lorentz transformation? And what does that mean in terms of space-time diagrams? So what I want to do here is that I want to be the last thing that I do here. And then we want to jump into the examples. And we're going to probably do about 3 or 4 examples once I get started here. So now I want to look at what does a Lorentz boost do in space-time diagrams. Okay, that's the question that I want to answer here next here. So let's keep drawing pictures just to make sure that we're seeing the same thing. So when I write a boost from here, we agree that what we really mean is that this implies that I write my coordinate shifts look something like this here. And my time shift looks something like this. Right? That's what I mean by a Lorentz boost. And I know that we've said this a whole bunch of times. What I really mean here is that I have some S frame, and now I have a frame S prime that has some velocity V. So that means relative to this frame, the S frame is at rest relative to some, let's say the Earth or something, and then I have that S prime actually moving away. So in the language that I've been using here, which I want to stop drawing pictures, we sort of have been drawing these things like this, right? And then I say, okay, here's Juan, right? And note that Maria is always moving, Juan is always on the rocket frame. I can't say that Maria is always moving because that's not RC. And so we typically say, okay, this is this frame here on the pale blue dot. And then of course we have the rocket that's moving in this direction. And we call this frame here the prime frame. And because the rocket's moving relative to Juan, we know that that's going to have length and time contraction. What do I mean by that? Well, in a space-time diagram, what it looks like is it looks like this here. So my red is Juan's frame of reference, and my green is Maria's frame of reference. And of course, I have my speed of light that all observers measure that. So now, when I talk about a Lorentz transformation, what does that mean? That means there is a time measurement. Maybe I should use black here. There is a time measurement. That means from the origin where the time is being made, there is a time measurement delta t. When I make this time measurement in Juan's frame of reference, and I boost to Maria's frame of reference, what do? I literally move along the coordinates of who? Juan's coordinates. And you could see that they're moving parallel to the x-axis. So a Lorentz transformation literally goes from this direction to that direction. Now note, there's no arrow because remember, the boost has infinite acceleration. So I'm literally boosting. And so when I go and I look at this time right here, that time here is delta t prime. And what you're seeing here is that for that time, there's also a spatial location. And so in this scenario here, I'm going to call this time t, delta t1. I'm going to call that delta t time right there. Now in the same space here, I got a spatial distance. So if I look at this, and this is the location of my spatial distance, delta x, then if I want to do a Lorentz transformation, then that means I'm boosting into what? The prime frame. And that distance here is then going to be this delta x prime. So in each of these cases, you're seeing this for the spatial transformation, but that's what it looks visually. And then I have this guy here going along the time axis. So note, I'm not indicating that these guys are the same. So I'm going to write that as 2 and 2 here, just to show you that they are not the same. Okay. Now I can do this for the other transformation. So for the other transformation, if I can do this here, I'm going to do just the opposite. So if I do just the opposite, I could go S prime going to S, and we already know that that means something very specifically. Right? It means this specifically. That's what I mean by that. So now this picture is different. So when I look at this picture, what we have then is that we have the same scenarios before. I have my pale blue dot, I have my rocket, but this time, because I'm now in her frame, she is at rest, and this guy is moving in the opposite direction. That's why we have the plus sign instead of the minus sign. And so when I look at this, I know that this is this frame right here, and I know that this frame is this frame. So in this scenario here, what do we know? We know that the Earth is moving relative to Juan. So when I go and I look at this coordinate system, what do the Lorentz transformations do? Well, drawing these somewhat quickly here, so if I look at this, the previous one had the grid system that was parallel to the T and X axis lines. So now what I want to do here is that they're now skewed. So if you look up here, the way I got time here is that I moved parallel to the X axis. So now if I want to do a Lorentz transformation, what I'm doing here is that I have to move parallel to the X prime axis here. So that means then I got to move at an angle. So if I look at here, this is my, oops, bad. I called that time. position. If this is my time, then when I go and I boost to this frame, I'm going to read whatever that delta t time is here.
See, but you can't like get out your ruler and measure on these axes.
But if you actually, you can, if you have, you can,
Like
if I
an
have,
inch on one axis is not the same amount of time as an inch on another one.
no. But what that means here is that you have to scale them.
Yeah.
If you actually do measure the scaling factors right, you have to do some scaling, right? And so that means you have to do some conversion factor. So if you do some conversion factor, then you get the right scaling.
Right, and there's only one special case where you can directly compare, which is when the two would be symmetrical, like
Yes, in the
Maria.
same inertial frame of reference.
One, yeah.
Yeah. And then if I want to go to the X position, then I have to move parallel to the CT prime axis. So then that means I got to move parallel to them when I get to here. And so therefore, that means that I'm moving along, I'm starting from here, which is delta X prime, and then I'm moving to what? Delta X. But that's exactly what a Lorentz transformation is doing here. Okay? That is what a Lorentz transformation is doing. And that's a visual way of actually looking at that. So to give you a sense of how you actually make some of these calculations, what I want to show you here is that I want to go in and look at a length and contraction and a time dilation and just really, really briefly show you here. So if I look at some example here, this is what the example should be here. So the first thing that I would do is that Juan and Maria are in the same inertial frames. Okay? They're in the same inertial frames. So that means here that I have 2 meter sticks. Maybe I should put them right on top of each other. And these meter sticks, what's special about them is that they have what? They have the same length. And because they have the same lengths, they both measure the same distances, and both of them say 1 meter. Now, what do I mean by clocks here? So in the past, what we've done here is that we've drawn this light clock. And when I think about a light clock, up here, I have a mirror. Down here, I have the source and the detector. Now, this becomes very painful to keep drawing again and again and again. So we don't want to do that. So I'll draw this one more time. So if I have a beam of light that goes up and down, the way I'm going to start to draw this is that I'm going to imagine a clock. And what I imagine with this clock here is that my arrow starts off at the noon, the 12 value, and what does this arrow do? It comes all the way around. Okay? So instead of drawing this scenario, this is nice and simple. So if I look at Juan's, and then I look at Maria's clock, these guys are ticking the exact same amount. So if I look at a pulse, a beam that goes up and down, that means that that's just 1 revolution. Now, if I had a clock that ran slow because of a mechanical default, then what do I mean by that? Well, then this clock does what? It's running slow, so it would do what? It would start here, and then it would come here, and then it would stop right there. So when I measure the time from T1 to T2, this time here is going to be less than that time, but we need to be more careful here. That means that this clock here takes longer for a full revolution. These clocks over here take less time for a full revolution. So we got to be really careful here. Now, the key word here that I'm really trying to stress here is that this is a bad clock. That's why that's happening. Clocks that are time dilated in special relativity are not bad clocks. What I'm saying here is that for this scenario here, I chose a mechanically defective clock to show you that it takes longer to make one longer revolution. Effectively, that's what we mean by time dilation, that it takes longer. So a time dilated clock takes longer for one revolution. Because this is a struggle for a lot of people right there. Okay? What that clock means. So now, here we go. Okay? And what we're going to do here is that they start in the same initial frame. Okay? So they're in the same So what does that mean? That means when I look at Juan's clock, it's going to be there after one full revolution. When I look at Maria's clock, it's going to be there after one full revolution. They rotate at the same rate. So now I'm going to have a frame where when I look at his clock, which is now the S frame, and then I'm going to look at the rocket's frame, we know that this rocket is moving, and as it's moving, we have this other frame, which is now this S prime frame. So what do we expect here? The fact that this thing is moving here, what we're saying here is we're saying that we expect from time dilation that Juan's clock is going to make one full revolution all the way around. While Maria's clock will not make a full revolution. It's going to take longer to make. So because of space-time, Maria's clock ticks slower than Juan's clock, right? That's what we mean. So by moving through space-time, the clock is ticking slower, right? And there's nothing wrong with Maria's clock. There is nothing wrong with Maria's clock. It's just that time implies that in space-time, time measurements are in the eye of the beholder. Different observers measure different times and both of them are right. It's not that our clock is better than theirs. It's just that time does not have objective reality, right? Which is really, really, really hard, right? No. Probably in the back of your mind, whether you realize it or not, if you're anything like me, you're probably going like, no, maybe their clock really is something wrong. Maybe as I run by Slack, it really is 2 miles long. The answer is, dude, that's your problem, not mine. You have the problem. You don't want to accept it, just like I don't want to accept it. Clocks tick slower when they move relative to an observer. If I compare both of them, they're going to have different values. So for the sake of argument, I'm going to assume that she moves at 80% the speed of light. Okay? So if she does that, then according to time dilation, right? So then time dilation implies what? Well, it says that Maria's clock, which is the prime, is going to have their clock of Juan is going to be time dilated. That means this is going to take what? It's going to take longer for 1 revolution. This is going to be, it's going to take shorter for 1 revolution. So in this case here, now that I have that, I have gamma, which will be 1 minus beta squared, which is then 1 minus 0.8 squared square root. And if you calculate that number, you get 1.67. So now I have my gamma factor. And if I have my gamma factor, then I look at this here then. Well, if I'm moving that fast, I know that, so in Juan's frame of reference, he has he has the proper time. And what does the proper time mean? That the clock is at rest relative to him. And according to this, a light clock travels 1 meter in this amount of time. And what's that amount of time? That means if I look at Juan's time, is then going to be about 3 nanoseconds. So if I look at Maria's time now, that means here that I gotta write delta t prime equals to what? It's gonna equal to delta t, times gamma. And so if I measure that, what that really means here is that this is going to be 1.67 times, by the way, I should be writing this with C's, which I didn't. And then this would give me times 1 meter. And so this gives me what? 1.67 meters, but we got to translate that into time. So if I calculate this into time for Maria, this will then be 1.67 meters divided by C. And this gives you a value of 5.6 nanoseconds. So Maria's clock is ticking what? Slower. It takes longer to make 1 revolution. Oh, damn. My alarm's going off. I'm over by 2 minutes. Dude, I gotta let go. I gotta go. Hey, moving right along here, right?